Hello everyone, welcome to Analog Electronic Circuits, lecture number 5. So we will continue on the last topic, whatever we have discussed. So let's start. So last time we started with the numerical, right, wherein we have to find the DC parameters, IBQ and ICQ, small signal parameters, GM and RPI, cutoff frequency due to external capacitors. So there are three external capacitors, CC1, CC2 and CE. Then the overall cutoff frequency, the midband gain in dB, and finally to plot the frequency response. The BJT parameters were given as beta equal to 100 and VB equal to 0.7, and we have been given a common emitter BJT amplifier employing a voltage divider bias. So we will just revise what we have done last time. So we have started with the DC analysis and we found out the values of VTH, RTH. VTH was coming out to be 4 volt, RTH is 8 kilo ohm, IBQ was coming out to be 15.71 microamperes, ICQ was 1.571 milliamperes. Then the small signal parameters, RPI was 1.65 kilo ohm and GM was 60.42 milliampere per volt. Okay. And since RO value is, we assumed RO value as infinite because VA value is not given, right? What is VAD? Early voltage value is not mentioned. And when we came to this part, that is drawing the low frequency small signal equivalent circuit, and last time we stopped over here. Okay, so let's begin and find out the individual cutoff frequency, FL of CC1, FL of CC2 and FL of CE. So let's begin this. Okay, so what's the procedure to follow up on the FL of CC1 low frequency equivalent circuit? The procedure is that we have to sort VS and we have to sort VS, then we have to sort CE and coupling capacitor CC2. We have already done that, right? Here the capacitor, bypass capacitor CE is sorted. Here the coupling capacitor CC2 is sorted. And now we will sort the VS. So if you do the analysis, we have done the analysis last time and we have found out that, the impedance offered, let's revise what we have done. So the impedance offered by this current source is infinite, right? So the entire left part of the circuit is gone. It's open circuit. So infinite means it's an open circuit. Okay, fine. So let's proceed forward. So here, let me little bit slightly. Yeah. So here we have to find out FL of CC1. So anyone remembers what was the formula for FL of CC1? So FL cutoff frequency due to CC1 was given by 1 upon 2 pi into R equivalent. Basically, this was R equivalent into CC1. And what was the R equivalent value? I'm not revising that why we have the how we have got this R equivalent. Last lecture, we have already discussed that. You all can refer that lecture. So R equivalent was given by R sig plus Ri, where in turn Ri was given by R1 parallel to R2 parallel to R pi. Okay, so that was the value for R1, Ri. Now we will calculate them quickly and we'll find out what's the value. So Ri value will be R1 parallel to R2 is 8 kilo ohm, right? Let's check that. Yes, R1 parallel to R2 is 8 kilo ohm. And over here we have R pi, which is 1.65. So let's put in these values over here. This is around 8 kilo ohm and this is around 1.65 kilo ohm. So what's the value of Ri? We will now determine. So Ri will be 8 kilo ohm parallel to 1.65 kilo ohm. Okay, how much is that? If you work out in a calculator, that is coming out to be 1.37 kilo ohm. Okay, so that's the value of Ri which we get. Now we plug in the formula and we'll find out the values of FL of CC1, right? Let me push this circuit below slightly so that we have enough space to work on the previous one. Let me just do that quickly. Okay, so I want to push this a little down. Yeah, done. So let's continue further now. Yeah, so let's go up and continue the remaining part. So over here we have FL of CC1. So R equivalent will be, let's find out R equivalent also. So R equivalent will be R sig plus Ri. Now what is the R sig value? I guess R sig value is given as around 1 kilo ohm. Let's confirm that. R sig value, how much is the value given in the numerical? Yeah, it is 1 kilo ohm. So we'll plug in that value over here and we'll find the value of R equivalent. So R equivalent is given by 1 kilo ohm plus 1.37 kilo ohm. So the answer is 2.37 kilo ohm. Okay, so that's the value of R equivalent for FL of CC1. And now we can easily calculate this. It will be FL of CC1 will be 1 divided by 2 pi into R equivalent is 2.37 K into CC1 value. How much is the CC1 value? CC1 value is 10 microfarad into 10 into 10 raised to minus 6. Okay, so that's the value of FL of, that's the expression of FL of CC1. Now, if you work it out in a calculator, the value of FL of CC1 will come out to be, so please calculate this. So is it coming out to be 6.71 hertz? If yes, then you are in the right track. So let me mark it over here. The value of FL of CC1 is 6.71 hertz. Okay, so everyone has followed what we have done over here. So for FL of CC1, we have short circuited VS, CE, and CC2, and we have analyzed the circuit and found out to be Ri and R equivalent. And then we have found out the FL of CC1. So we got the answer as 6.71 hertz. Now we will proceed ahead and we'll follow up the calculation for FL of CC2. So for FL of CC2, what all things we do? We first of all short circuit. We have done this last time, but still I'm repeating. We short circuit VS, then we short circuit CC1 and bypass capacitor CE. So let's do that over here. Short circuit VS. So VS source is equal to 0 and impedance offered by this current source is again infinite. That means it will be replaced by a open circuit. So if that happens, the entire left part from the emitter base part circuit is gone. It's open circuited, right? So what is left out with us now? So here if I want to write the formula of FL of CC2, it will be given by, can anyone tell me directly? 1 divided by 2 pi into R equivalent into CC2, correct? And over here, what is the R equivalent? R equivalent will be RC plus RL, not parallel to RC plus RL. So kindly note that it is plus, not this other way around. And this RC parallel to RL, the R equivalent, let's find out. So R equivalent is, RC value is 4 kilo ohm. So 4K plus RL is 2.2K. RL value is 2.2K. So R equivalent will be how much? 4 plus 2.2. That will be 6.2 kilo ohms. So in this case, the R equivalent is coming out to be 6.2 kilo ohms. So let's find out the value of FL of CC2. It will be 1 divided by 2 pi into 6.2K into, now value of CC2 is 1 microfarad. So 1 into 10 raised to minus 6. it's always important to write this expression. Don't directly solve it in your calculator, right? Once you write it, then you can solve it. So FL of CC2 is coming out to be, if you work it out in your calculator, it's coming out to be 25.67 hertz. So please verify this, 25.67 hertz. So you can please check out the calculations in a calculator. So calculation of FL of CC2 is very simple. It's 1 upon 2 pi into RC plus RL into CC2. And the value we got it as 25.67 hertz. Now let's turn our attention to calculation of FL of CE. Now FL of CE was slightly complex, but we have managed it last time. So again here we have to short circuit VS. We have already done that. CC1 and CC2. So already it's been taken care. Only the VS can be short circuited. So this is the low frequency response for, okay, sorry for that. Yeah, this is the low frequency small signal equivalent circuit for calculation of FL of CE. Okay, so what was the formula? Anyone remembers? Okay, no problem. We have revised it last time, but still. Okay, let me use black color over here. So FL of CE is given by 1 divided by 2 pi into R equivalent into CE. And the formula for R equivalent was something like this. R equivalent was given by, it was a huge formula, RE parallel to, and then inside we had, let me go slightly this side, we had R sig parallel to R1 parallel to R2 plus R pi. This we have derived it last time, the whole divided by beta. Okay, so this was the formula. Let me do that again. Okay, yeah, it's complete now. Now we know the value of R1 and R2. So the value of R1 and R2 is around 8 kilo ohm. Okay, and the value of R pi is 1.65 kilo ohm. The value of R sig is 1 kilo ohm. The value of beta is 100, and the value of RE is 2 kilo ohm. Fine. So we have to find the value of R equivalent and then put it in the formula. So it's coming out to be, if you work out in a calculator, you're getting the value of R equivalent as, so R equivalent is equal to 2 kilo ohms parallel to, here if you check it out over here, this 8 kilo ohm parallel to 1 kilo ohm will give you 888.88 ohms, and this is 1.65. So that is coming out to be divided by 100, that will be 25.438. So we know that a larger resistor parallel to a lower resistance, so R equivalent will be smaller than the lower resistance. So R equivalent is coming out to be over here 25.118. Okay, so that's the value we got it for R equivalent. Please confirm your answers whether your answers are matching with this results. Okay. So now let's proceed forward. So from here we can calculate FL of CE. So FL of CE will be given by 1 upon 2 pi into R equivalent. R equivalent value is 25.19. We can consider approximate into CE. The CE value is 20 microfarad. Okay, that means 20 into 10 raised to minus 6. So what's the value of FL of CE? Substitute the values in the calculator, and 1 upon 2 pi 25.19 into 20 microfarad. So this value is coming out to be 136.81 hertz. Okay, so yeah, that's the value of FL of CE which we are getting. Let me write it hertz properly. Yeah. Do remember that whenever you write a numerical value, it should be supported by the proper unit. Okay, R equivalent, FL of CE, all should be supported by proper unit. Now next comes the calculation of FL. Let me push it slightly up. Next steps comes the calculation of FL. Now what is FL basically? FL is the overall cutoff frequency, lower cutoff frequency, right? So FL will be given by maximum of FL of CC1, comma, FL of CC2, comma, FL of CE. Now it's very clear from our analysis that among the three value of FL of CC1, CC2, and CE, the value of FL of CE is the highest value. So over here we can say that FL is given by 316.81 hertz. Okay, the maximum value out of the lot. So let me put it inside the box because that is an important number. FL, the lower cutoff frequency. Now what is FL? It is the lower cutoff frequency of the amplifier. Okay, it is the lower cutoff frequency of the amplifier. Fine. Now we have calculated FL. Now next thing is calculation of AV mid. Now remember, while we have earlier we have denoted this small mid frequency equivalent circuit, right? So we can see all the coupling capacitors are replaced by a short circuit, right? So let's start with the analysis. So here this is Vs. So this will be V in. Okay. So from here to here, this will be V in. Fine. So remember earlier in the very first lecture, we have bifurcated what is the source. So this is basically the source. Okay. And this part over here, sorry for that. This part over here is the load. And in between we have the amplifier. We have done this for the main circuit of common emitter amplifier. So this part over here is my amplifier part. Okay. So now if I have to denote the voltage gain, so if I want to write the formula for AV mid, the voltage gain at mid frequency or at mid band. So it should be denoted by total output V out, because here V out is AC quantity and Vs is also a AC quantity, a small signal. So it's given by V out divided by Vs, which can be in turn written as V out divided by V in. So it can be written as V out divided by V in into V in divided by Vs. So it means the same. So individually we have to find it out. Okay. Now, if you look carefully over here, V out upon V in can be easily calculated. Correct? How? So V out divided by V in. See, V in is the voltage applied to the base terminal, right? V in is parallel to V pi, right? It's very clear, that very evident. So V out upon V in, already we know it for common emitter amplifier. Its formula is given by minus GM into RC parallel to RL. Okay, let's see how do we got it. I know that you all know about it, but let's discuss this in brief. So basically, what will be V out given by in this in this circuit? V out will be given by the current flowing through the the collector to emitter. So basically, collector to emitter current is called as IC, and that is denoted by GM into V pi. Correct? So what is V out given by from here? V out will be given by two parallel resistance, RC parallel to RL into IC, into minus of IC, because it's moving out of the terminal of collector. So V out will be given by minus IC into RC parallel to RL. And my IC is nothing but minus GM into V pi into RC parallel to RL. So that's the value of V out. Now, what is the value of V in? So if you see carefully, V in is parallel to V pi. So I can write over here, V in is equal to V pi. Now, if I divide V out by V in, V pi and V pi will get cancelled, and I left out with GM RC parallel to RL minus GM RC parallel to RL. Okay. So that's how we get the value of you know V out upon V in. So let's calculate that. So V out divided by V in. So what was the value of GM given to us? I think the GM value was 60 point something. Let's see that. I think it's 60.42. So it will be minus 60.42 milli. So that means 10 raised to minus 3 and into RC parallel to RL. So RC is basically how much? It's 4K parallel to 2.2K. Okay, 4K parallel to 2.2K. Now this number, if you do it in your calculator, this will be like around 1.42K. Okay, so 1.42K into 60.42 into 10 raised to minus 3. What will be the result? So V out divided by V in will be it's coming out to be minus 85.75. Okay, so that's the value which we are getting for the V out upon V in. So many students make a mistake and consider this as AV mid. This is not AV mid. This is V out upon V in. What is AV mid? V out upon Vs. So next we have to find out what is V in upon Vs. Okay. So next we have to find out what is V in upon Vs value. So if I redraw this part of the circuit, Vs, R sig, and in series we have R1 parallel to R2, and we have R pi in parallel. Okay, these R1 parallel to R2 parallel to R pi is all they are in parallel, right? So if I have to write it in this form, I'll write it as follows. I am representing the circuit over here. So this is Vs. This is my, let me add it like this. This is R sig. And over here we have three resistance which are in parallel. R1 parallel to R2 parallel to R pi. Okay, clear about it? This is the ground. And over here we are testing out V in. So this is V in. So this is a simple voltage divider. We can use a simple voltage divider. So we can write by voltage division rule. What can we write by voltage division rule? Let me just take it up. So what we can write? We can write V in. If I want to write V in, that will be this resistance R1 parallel to R2 parallel to R pi divided by R1 parallel to R2 parallel to R pi plus R6 plus R6 resistance. So do we have the parallel combination value R1 parallel to R2 parallel to R pi somewhere before? Have we calculated it? Let's see that. I guess yes, we have calculated that before. I think in FL of CC1. Okay, sorry for this. Yeah, R1 parallel to R2 parallel to R pi, its value is 1.37. So that is 1.37. So we'll come over here and we substitute that value. Okay, and this is into, okay, this will be into Vs. So this Vs we can bring it out over here. Okay, so hence we can do that. This Vs will bring it out over here and this will go in the denominator. So V out upon Vs will be equal to 1.37K divided by 1.37K plus 1K, 1 kilo ohm. And how much is that value? Please calculate and let me know. This value is 0.578. Now many people don't calculate this value and directly treat the V out upon V in as the final voltage gain, which is wrong. What is the final voltage gain? AV mid. Let us rewrite. So AV mid will be given by V out upon V in. The value is minus 85 point. How much is that? Okay. Let me check it out over here. 85.75. So 85.75 into 0.578. So that much is the value for your AV mid. Okay. So let us calculate this. You multiply this simple multiplication and you will get it as minus 49.56. So that's the value of AV mid. Okay. This is the value of AV mid which we want. Now, if I want to, I want the value of AV mid to be in dB. So the value of AV mid in dB can be calculated as 20 log to the base 10. Now here we have to consider mod of AV mid, right? Because logarithmic will not take negative value. So you will get 49.56. So please calculate this number. 20 log to the base 10 of 49.56. What's the value? This value comes out to be 33.9 dB. Okay, so the value of AV mid is coming out to be, let me write it down again below, because that's an important number. So I'll write it again over here. AV mid in dB is 33.9 dB. So that's the value which we are getting. Let me put it inside a box. It's an important result. So this is my midband voltage gain. So we have calculated FL and we have calculated AV mid. So even if they don't ask you DC analysis, we have to calculate RPi and GM without even asking, because it will be required for AV mid and FL calculation. Now, final step is to plot the frequency response. We know that all FL1, FL2, and FL of CC1, FL of CC2, and FL of CE will support the kind of graph which looks something like this. Okay, so let me take black color and plot the graph like this. Okay, so let me try it one more time. Yeah. So here in the x-axis and y-axis, we can write over here, this will be AV mid in dB. This is AV mid in dB, and this will be frequency, which is in the log scale. Okay, and when we plot the graph, it looks something like this. Okay, and the maximum value over here, how much is the maximum value? Let's calculate. Let me mark it first. Okay, we have taken slightly up. This is the maximum value. So this maximum value is my voltage gain in AV mid, right? And how much is that? That voltage gain is 33.9 dB. So let me write that value. This value over here is 33.9 dB. Now anyone knows how to plot FL, the lower cutoff frequency? So you have to go 3 dB down. Okay, wherever it intersects, now make this marking towards the x-axis. So this is my FL. Okay, so how you do it? You go 3 dB down. So this is 3 dB down. Okay, so when you go 3 dB down and mark it on the y-axis, that will be FL. And what was the value of FL which we got? It was 316.81 hertz. Okay, so that is the value of lower cutoff frequency of this BJT amplifier, and this is my frequency response. Okay, and 3 dB down, this value, if you want to write, if you wish to write, it will be 30.9 dB. So at 30.9 dB, the corresponding value of the FL will be 1316.81 hertz. Okay, and this completes the entire analysis for this numerical. So we have completed this numerical of BJT amplifier, and I hope that all the things are clear to you all. Now let's move on to the next one, the new one. Let's move on to the new numerical. Okay, fine. So yeah, so let's continue further now. So this is second numerical. So immediately if you see the circuit, this is a common emitter amplifier. with R1, R2, RC, RE, CC1 and CC2. Remember, CE is not there. So it is common emitter amplifier without bypass capacitor. Okay, RSig is there, RL is there, BJT parameters have been given, beta is 200, VB value is 0.7 volt. So again, we have to calculate the similar set of testings parameters such as IBQ, ICQ, RPi, GM, FL of CC1, FL of CC2, no FL of CE over here, then lower cutoff frequency FL, AV mid in dB, and finally we have to plot the frequency response. So let us start with the DC analysis part. Now I hope that this will be familiar. This is for your voltage divider bias. Let us check the values first of all so that we can confirm. VCC value is 10 volt, RSig value is 100 ohm, CC1 value is 47 microfarad, CC2 value is 4.7 microfarad, RE value is 100, RC value is 2 kilo ohms, R1 value is 20 kilo ohms, R2 value is 2.2 kilo ohms. Okay, so these are the values of resistors and capacitors inside the circuit, and beta value is 200, VB is 0.7. So let us start with calculating calculating VTH. So VTH is R2 upon R1 plus R2. So that will be 2.2 kilo ohms divided by R1 value is 20K. So 20K plus 2.2 kilo into 10. VCC value is 10. And this value comes out to be close to 1 volt. Okay. So this value comes out to be 1 volt over here. Now next is R1 parallel to R2, which will be 20 kilo ohms parallel to 2.2K. So if you work out in a calculator, you will get a value lesser than 2.2, which is 1.98 kilo ohm. So RTH value is 1.98 kilo ohm. Please check it in your calculator. Don't just write this answer. Okay. Next is IBQ formula is VTH minus VB. So VTH is 1 volt minus VB, that is 0.7 divided by RTH value is 1.98 kilo ohms plus beta value is 200. So it will be 201 into the value of RE is 100. Okay. So if you work out in a calculator, you will get the value of IBQ as, let me write it over here, it will be 13.58 microamperes. Okay. So please check this answer. IBQ, we are getting it as 13.58 microamperes. Now next, let us calculate, over here we have beta, which is 200 into IBQ, which is 13.58 microamperes, which is into 10 raised to minus 6. So this number, ICQ, the collector current will be 2.72 milliamperes. Okay. So the current value over here, let me write the numbers properly. 2.72 milliamperes is the value of collector current. Why we require ICQ? Because once we know ICQ, we can calculate the small signal parameters. So over here, we will write down beta, which is 200. VT value, we have to assume it as 26 millivolts. So that's 26 into 10 raised to minus 3. Then we have ICQ, which is 2.72 into 10 raised to minus 3. So this minus 3 and this minus 3 gets cancelled. And we get over here RPi value should be equal to 1.91 kilo ohm. Okay. So RPi value is coming out to be 1.91 kilo ohm. Now, next is GM. GM is given by ICQ divided by VT. So that will be ICQ is 2.72 into 10 raised to minus 3. And VT value is 26 into 10 raised to minus 3. So again from here minus 3 gets cancelled. And we have over here 2.72 divided by 26. So this will be around 104.61 milliampere per volt. Don't forget to write the units properly. Okay. So please cross check these values of ICQ, RPi and GM. What about RO? Small RO. So small RO, we will assume it to be infinite, since VA is not given. Okay, RO is assumed to be infinite since VA value is not given. Okay, so we have found out the values of R pi and GM. So next, let's go to the frequency response. So this is my low frequency small signal equivalent circuit with all the capacitors in the circuit. Now we have to do the calculate the formula for the expression for the FL of CC1. So let's proceed and calculate the, you know, FL of CC1 expression. So for FL of CC1, what we have to do, right? We have to, first of all, let me write it over here. We have to short circuit VS source and CC2. So we have to short circuit VS source and CC2 value, right? So let me draw it over here. Now, again over here, if you see carefully, if you see carefully in this circuit, the impedance offered by this current source, GM into V pi, again will be infinite. So this will be again into infinite. The impedance looking into the current source will be infinite. That means the circuit connecting the collector part will be open circuited. It will be completely gone. Okay. So right now our main circuit will be just this much. Let me draw it. I mean, let me mark that point. So this much is the circuit remaining with us. Let me take it. Okay, so this much is the circuit which we have to work with, and over here we have CC1 capacitor connected. The VS should be short circuited. So this is actually connected to the ground. Okay, fine. So now let us analyze this part. Now, do you remember this is similar to what we have done before, right? Let me just refresh the memory. So let me draw the voltage source VS and then the internal resistance R sig. Then we have a capacitor CC1 and then this is connected to a system. So this is my system. Okay, let me just okay, so this is the system which we are talking about, and for this system we have to calculate the input impedance or input resistance. So let me take another color. So here we have to calculate Ri, right? And how do we calculate FL now? FL of CC1, FL of CC1 will be 1 upon 2 pi R equivalent into CC1. The formula remains the same. And what is R equivalent? That also remains the same over here. R equivalent is nothing but Ri plus R6. Okay. So R equivalent is Ri plus R6. So we have to calculate Ri now. Now Ri is what? I think this part of the circuit, right? Here we have it. Let me just try to delete this. Okay, fine. I guess inside that we have to look into this circuit. Okay, so let me push this part a little that side. So let me redraw it like this. Here I have a capacitor CC1. What I'm really trying to make the point is that in this circuit, inside that also, where we have to apply the where is the system? Our system is this the green part. So this is the system which we are talking about, right? And over here we have to find out Ri. We have to find out Ri of this system. Okay, understood, right? So let's proceed forward now. So what is the Ri looking into the system? Only this much is there. R1 parallel to R2 and R pi, right? So R1 parallel to R2, it is parallel to R pi plus Re. Now whether we can write it as it is? No. The reason being is that here the current which is flowing into the base terminal is IB. This current is IB. And the current flowing into the emitter terminal is IE. Now, how they are related to each other, IE and IB? They are related by the following formula. So, IE is 1 plus beta times IB. So, if I have to write and consider RE, which is in series with R pi, the current, all the current should be in the base current form. So, I will replace IE by 1 plus beta times IB. So, how can I write RI now? RI can be written as R1 parallel to R2, and that is parallel to R pi plus, okay, R pi plus RE, not RE. 1 plus beta times RE, because here the emitter current changes to the base current if you multiply by 1 plus beta. So here I have multiplied 1 plus beta times, okay, let me change that, 1 plus beta times RE. So this is the correct formula now of RI. Okay, now we have less time. I am directly giving you the value of Ri. So Ri, if you calculate and plug in the values over here, you will get an answer close to 1 point. You will get an answer close to 1.816. Okay, let me rewrite it. The value of Ri will come out to be 1.816 kiloohms. Okay, and let me mark it over here. Ri is 1.816 kiloohms. And what is RSig value? I think RSig value we have taken it as the RSig value was 100 ohms. Okay, so from here we can easily calculate the value of R equivalent. So R equivalent will be Ri is 1.816 K plus RSig, that is around 100 ohms. Okay, so that will be you can calculate it, and from here we can easily calculate the value of FL of CC1. Okay, so from here FL of CC1, now we have a little short time, so I'm directly giving you all its value will be, let me rewrite the formula. Okay, 1 upon 2 pi into here we have 1.916 K, okay, into 47 microfarad. We had CC1 value as 47 microfarad. So I'm using this formula over here. Okay, R equivalent came out to be 1.916 K. Okay, and the final result FL of CC1 will be, we can check it out over here. FL of CC1 will be equal to 1.767 hertz. So that's the lower cutoff frequency due to input coupling capacitor CC1. So yeah, we are just falling short of time. So that's why we are calculating this. So y'all can verify this answer on your own. Okay. Now let's move our attention to calculation of FL of CC2. So for FL of CC2, what do we do first? We will short circuit. We have to short circuit VS and CC1. Okay. So we'll take from here VS. This is actually CC1. We'll replace it by a short, right? And this also VS, will replace it by a short. Okay. Now again, same thing will happen over here. The impedance offered by this current source will be infinite. That means it will be replaced by an open circuit. So if that is replaced by an open circuit, the entire circuit from base to emitter will be open circuited. From collector to emitter side to the left hand side will be open circuited, right? And what are we left out with? This is actually CC2. Okay, CC2. Fine. And what are we left out with? Very simple. We have on the right hand side of the capacitor RC. On the left hand side we have RC. Right hand side we have RL. So how can we write this formula? FL of CC2 will be 1 upon 2 pi R equivalent into CC2. And what is R equivalent over here? R equivalent is RC plus RL. Remember, it's not parallel, it's RC plus RL. And we can easily calculate that RC now. In this case, we have RC as around 2K and RL is around 1K. Let's cross verify that once. Okay. Yeah, RC is 2K and RL is 1K. Yeah, it's perfect. So let's continue with the FL of CC2 calculation. So this will be, let me switch it again. So this will be 2K plus 1K, which is 3 kilo ohms. Okay. So our equivalent value is 3 kilo ohms. Now we have to substitute it over here. CC2 value is given as 4.7 microfarad. So FL of CC2 will be 1 upon 2 pi into 3 kilo ohms. Okay, what do you mean by 3 kilo ohms? 3 into 10 raised to 3 into CC2 value is 4.7 microfarad. So 4.7 into 10 raised to minus 6. So if you work it out in a calculator, you will get the value of FL of CC2 as approximately equal to 11 point, sorry for that, 11.287 hertz. So that's the value of FL of CC2, right? So the next step, this is with step number 5. So next is the step number 6. So in the step number 6, we have to do the calculation for, okay, it's about the calculation of the lower cutoff frequency FL. Okay, so what? How do we get the lower cutoff frequency? So FL will be the maximum of sorry for this. FL of CC1, comma FL of CC2. And we can definitely make out that FL of CC2 is 11.287 hertz and FL of CC1 is around 1.767. So we can easily determine that the higher cutoff frequency is equal to FL of CC2. I mean lower cutoff frequency. So FL will be given by 11 point. Let me just write it again. 11.287 hertz. Okay, so that's the value of FL which we are getting, the lower cutoff frequency. Okay, so FL value is coming out to be 11.287. This thing is little bit stuck. So just wait until it's responding again. So we have calculated the lower cutoff frequency of the amplifier in the form of FL. Okay, FL is the lower cutoff frequency. And how do we decide that lower cutoff frequency? It will be the maximum of FL of CC1 and FL of CC2. I guess I might have to restart the value, restart the Microsoft Word, because it's not responding right now. So let me just start it again. Just a moment. I will be sharing that one more time. Whiteboard. Okay, please bear for a few seconds. Okay, I guess the screen is shared again now, the Microsoft Whiteboard. I hope it is visible. Okay, sorry for that. Yeah, so let's continue where we have left before. So we have calculated the lower cutoff frequency. We have calculated the lower cutoff frequency, which was given by FL, and we were about to put it inside the box. Okay, so FL is basically the low cutoff frequency, of the amplifier. Okay, low cutoff frequency of BJT amplifier, of given amplifier, right? Of given BJT amplifier. Okay, so we have come to the end of this session. Next step is basically step number 7 is calculation of AV mid, which is the lower cutoff, the mid band voltage gain. So that we will cover next time. So this calculation of AV mid, now we have almost time up. So we will continue next time. So that we will continue in analog electronic circuits, lecture number 6.1, lecture number 6. Okay, so we'll stop over here. I'll stop the recording, and we have completed up till the lower cutoff frequency. Next time in the lecture, we'll start with the calculation of AV mid. Okay, so that's all for this session. Thank you for joining, and next time we'll start with the AV mid calculation and complete the numerical. So until then, have a good day and thank you.